So welcome back, and let's talk about adversarial examples as one way for local explanations. As learning words, we have again three today. First one, of course, we'd like to understand more the definition. What is actually an ADE, which stands for, of course, adversarial example. And we'd like to understand first methods that generate these kind of adversarial examples and discuss potential causes for these ADEs and their defenses against them. So let's directly dive into it. So what is adversarial machine learning actually? So let's first start to consider what actually happens if a computer system or machine learning system, let's say, gets an erroneous input, right? If something is wrong and not what we like to expect to that. Or even worse, what happens if someone feeds in a malicious input on purpose to attack a system? And of course, you'd like to ensure some kind of robustness, which then leads to safe services, right? So someone would like to attack your system, to attack your machine learning model, like that machine learning model is not returning something completely arbitrary to that, but that really your user can have trust in it. And at the same machine learning side is the robustness of machine learning algorithms to these kind of malicious input. And two different kinds of attacks. Evasion attacks, which mislead an employed machine learning model with manipulated inputs. And that's the focus actually of that kind of video today. And there's also data poisoning. So that has malicious input already in the training data set. We're not covering that, right? Because we're talking here about local explanations. We like to see actually what happens if you feed in a certain input vector, a certain input to your machine learning model. What does it really mean for a trained model, right? We don't really covering here what it means for the training of the model and therefore also not about the training data set. So let's start with actually an informal definition for an ADE. And so an ADE is an input to a model that deliberately designs to fool the model into misclassifying it, right? So it's not like it happens somehow, but it was really designed to it, right? That's very important that we emphasizing that part. Even if we have models actually with low generalization error, where I believe in most cases actually the model will do what it should do, nevertheless there can be adversarial examples, which is of course not a good thing for machine learning in general. Both deep learning models, for example, convolutional neural networks or others, and also classical machine learning models can be vulnerable to such attacks, which really shows that it's a problem in general. ADEs created from a real data observation X, so really again an input vector, for example, an image or tensor or whatnot, can be indistinguishable from X by human observer, right? That's often the case, that really emphasizing that we as a human would not see that someone really changed something in the input. Nevertheless, the model will misclassify that kind of slightly changed input. So that means that maybe your model doesn't really have a real understanding of the underlying concept of the provided inputs, but is really now trying to make shortcuts which are unintended. Here, a very famous example, for example, if we'd like to contain an image classifier again and say, yeah, okay, it was able to recognize that's a duck, but now we're adding some little noise on it, right? And with a small weight on it. So if you would do that, then for us, that image looks more or less very much like that, right? So there's a little bit more noise on it, but overall we would still see it, that's still a duck. But now your image classifier says that's a horse. So that's a real problem, right? And of course, it could be also done with audio data. So maybe we have an audio recording of how are you, adding a little bit of noise. This is a very small factor again. So if we're comparing that one with that one, you see little differences over here, right? We see a little bit of noise added. But overall, you would be able to understand, even with a little bit of noise, that's how are you, and not opens the door. Let's have some examples on further image data, right? We have seen that already before, that If you're adding patches to stop signs, it will be misclassified. If you're adding maybe also graffiti to that, it will maybe lead to misclassified predictions. So really, we have a problem over with that. But it's even worse. People showed that they were able to use a 3D print of a turtle. So you can see that actually, that's a very nice image, which comes with a problem that the image classifier was very certain actually that's a rifle, that's a gun, and even from different kind of angles. So if you're taking shots of that kind of turtle, it will often say that's the rifle. And that's very weird, right? For us, it's very obvious. And it seems like that the model was not learning what it was intended to learn. Of course, that also applies to tabular data. It's maybe not so obvious now how that goes in that direction. But let's say you would like that you accept that the bank was accepting your loan application or was detecting that, right? And now we have maybe two inputs. One is your salary and one is how many pets you actually have. Let's say we're talking about that input point over here. Maybe let's change the color and you can see it maybe better, right? So it's very obvious for you saying, yeah, if you would now increase your salary, there's a higher chance for you getting the loan actually. But it's a bit weird to say that if you now increasing the number of pets, you're also getting the loan, right? But not quite. The model has not quite learned what you would believe is important. And that's the underlying idea again, saying expert would focus on the most important features in the judgment, and maybe a machine learning model also put some weight, maybe even it's the small weight, on some more or less important things to do, right? So how does now an ADE relate to interpretabilities? Quite simple, saying that ADEs show where the model fails, right? And that should improve your understanding, because now you can really go and check, okay, for that example, it was not doing what you extended to do. Can we fix it? Do we need more training data? Do we need a different architecture or whatnot, right? On the other hand, also because of ADEs, we need more interpretability, right? So if we know that's failing, we would like to know even more why it was failing, when we see more of these techniques in upcoming videos. And interpretation can lead to robustness against ADEs, right? If the moment you're starting to understand, you improve your models, and hopefully that's hard to generate these ADEs. Even explanations can be used to construct ADEs, right? So if you know from the previous slide that that's going to happen over here with the number of pets, then you can start to rebuild your model, saying that, okay, it should not follow that kind of trend, but maybe different kind of trend. Say that maybe the should more like a very linear model over here, right? Okay, so let's go to a more formal definition of what is an adversarial input, an adversarial example. And for that, we're saying that we have a machine learning model called F. F, of course, goes from some kind of input, X, to some kind of output label, maybe Y. So we have domains, and we have a very concrete real data point that is correctly classified, right? That's the assumption that we're starting with a correctly classified one. Or we can also say that if you're putting X into our machine learning model F, we would get really the true correct label Y. So now we're saying that A subscript X is an adversarial input to X if the following condition holds. We're saying that A of X, the difference to X, so the distance more or less to each other, is fairly small. We're saying there is some kind of an epsilon. The epsilon is, of course, then maybe chosen by some expert what kind of epsilon it is. But in the end, we're saying A of X, so the adversarial input, is very close to our original X. Nevertheless, although it's very close to that, we're saying that now our machine learning model F is not returning the correct label anymore, right? So here, that's unequal. So we have to say then, if that's really happening, then something is weird, right? So now the question is only that we have to think about that part, about how to get these very small changes of x in a way that we don't obtain the true label anymore. So there are some hypotheses actually on why ADEs exist. Let's discuss some of these. There could be lower probability spaces of hypotheses. So maybe we're seeing here different kind of classifiers. So we have binary classifier example. So the dark blue versus the green dots we would like to classify in that example. And we care about what happens actually about just these kind of points, saying that we're starting over here and making these small changes, epsilon in the direction. And the dotted line represents the true decision boundary, but what we actually learned, because it was nevertheless still reasonable, was the solid line, right? That's F for us. And of course, the dotted line would be much better, but we don't know that, right? So what now we'll do by applying our adversarial example, the light bluish, grayish dots here, we see that it's on the wrong side of the decision boundary if we see the dotted line as ground truth. And the reason is simply because given the data we have over here in that image, right, we could have different kind of possible hypotheses, right? So that it could be different kind of models. And some would be more vulnerable to adversarial examples, much less, since we can't cover the entire space, of course. What should we do? Second hypothesis is the linearity hypothesis. And that's one of the most popular one. It goes already back to 2014. And that's the saying that adversarial examples are omnipresent in the data manifold, right? And that's the reason because in that data manifold, we have often very linear behaviors. Could, for example, also be the way we train our models, the reason for that. And if we have these kind of linear behavior, that simply means that small changes of epsilon in every feature causes a quite change in the overall prediction, right? So if we have always an epsilon change in all kind of features, and we have maybe many of these, think about images again. Each of your pixels is one of your features, right? And if you're always adding a small bit of noise to it, that will change quite a bit, right? So if we have here these kind of linear model, x transposed theta, now we're applying our epsilon to x. Of course, the difference is epsilon times theta to that, right? So it's not small actually, and depends on your weights of your model then. Then there's also the boundary tilting hypothesis. So linearity is neither necessarily nor sufficient to explain ADEs actually. This was shown in 2016. And ADEs mostly result from overfitting the sample manifold, right? And that's always a bit of a problem if you're going to deep neural networks, right? We like to do some kind of overfitting, so we really train for a long time. Even if training error goes to zero, we still try to continue training actually. And that sometimes leads to good things and sometimes to less good things. And now if we're saying that we have here these image manifold, and the red one is actually here the standard decision boundary. But if we're looking more closely to that, in the manifold, of course, we would like to really have a good decision boundary with more like slicing in that way, right? And of course, again, we have here different kind of ways for doing that. So like how you tilt that hypothesis, the decision boundary now, brings you to different kind of ADEs and therefore also different kind of robustness. So there's one more hypothesis, which is a more human-centric hypothesis. And that's saying that machine learning models make use of predictive but non-robust features. And simply that's how they're designed, right? So we're simply giving them all kind of features we believe could make it impact, but actually then human expert from the domain would maybe use less of that, and by case study actually also changing what is important or not. So they maybe, so the machine learning models maybe have highly correlated non-robust features in making use of for predicting the target. But human would maybe not in that case. So let's talk about ways to generate ADEs. There are different ways for constructing ADEs actually. There are, we will only discuss some of them here, of course, in that kind of short lecture video. And the important first insight is saying we treat that as an optimization problem, right? So saying that we have an input x, so x is fixed, right? So we're starting from that. We'd like now to find is x prime in our input feature space in a way that that gets fairly small, that part, right? So we would like to minimize the distance. And on the other hand, of course, the prediction should be different, right? So we would like to find some kind of x prime where we're getting now a different kind of prediction. We can here use sensitivity analysis to the differential that influence the target class, which makes it then, of course, simpler to find x prime. And one way also for doing that in the deep learning space, that's the reason why I was saying earlier that there's some work already from 2014 are generative adversarial networks GANs. Moreover, depending on the attacker's model access, we can also distinguish between two different kind of things here. So the full access attack, that means the attacker really has all the knowledge about your internals of the model, knows all the ways of a deep neural network, knows the architectures, everything more or less about that, right? Which makes it much easier, of course, to do that in an adversarial attack if I have full access to that. But also, even if we have only black box access, that means we can only query that. It means that we can only get predictions for certain inputs, and we can still try then to find x prime, right? So that kind of definition over here is actually a black box view in that, right? Because we can change our input to x prime and we can get predictions for that new input. So let's talk about a very concrete one. That's the fast gradient sign method, FGSM. Goes also back to Goodfellow in 2015. And that's actually saying, yeah, let's say we have our x, like to change it slightly, and now we only need to know actually in which kind of direction we need to do that. So that's now then random noise. And would like to say, yeah, let's look at the pointwise sign of the gradient of cost function j in x with our true label, right? So what would actually change, or what kind of direction we have to follow the gradient information of our model in a way that we will change simply our prediction, right? That's all it's doing, right? Saying in which direction I have to apply now my noise to say we go from a panda to a gibbon. So that's a very easy and straightforward way of putting it. Notes on FGSM saying that that works very well actually in case for these kind of linear-like, more or less nine-dimensional spaces, like SEM, regression, CNNs with redo activation functions, for example. There it's fairly easy to find these. Nevertheless, not every of our generated now x prime or ax but generated by FGSM is an adversarial example, especially if epsilon is too small, right? Because what we really need is making epsilon large enough in a way that the label is changed, and nevertheless we still saying for human it would not be obvious that there's a change in the input. Of course, here we assume that we have this kind of gradient information over here, right? That means we need access actually to a true model, but of course we can also try to approximate that, right? So even if you only have black box view on that, we can use finite difference methods, so doing small changes on x to get to x prime, and then simply by doing that approximating our gradient. So of course more expensive, so you need more compute power if you're doing that black box, but nevertheless possible. The notion of similarity of HTMLS is based off the infinite norm, but nevertheless you can also generalize actually that attack to other norms if you like to. So we already started to talk about black box attacks with here, and there's also a way to do this with surrogates, which goes to 2016. So let's say we have only these kind of query access. We can only get certain predictions for certain inputs, but we don't have the internals of the models. And that's often the case really in application, right? So you would like to deploy a machine learning model to your customer, and of course, they can start to query that now. That's a large risk, simply, because now your customer can query that. Of course, you can try to limit the number of queries, but nevertheless, there's some amount you need to make available. So what you're doing is you query your model you aim to attack as often as allowed on data similar to the training data. Right now you're starting to get some kind of information about the machine learning model you would like to attack. So now you start to understand actually how the decision boundary maybe looks like, and using that kind of data to imitate now the machine learning model, which means you now train a surrogate model. Right, so you're doing it really on top of the original machine learning model by simply querying that, simply trying to imitate that. And then you generate an ADEs for the surrogate model in the hope that the surrogate model is accurate enough of the underlying machine learning model you'd like to attack. And then you, of course, simply use that to directly attack the original models. And of course, you can have a feedback loop in case it was not successful at the beginning and trying to improve over time. And that's actually known as transferability of ADEs. So often, if you have a sufficient amount of queries of the original models, a surrogate model might be accurate enough to really show you where you can attack your original model. And that's, of course, a big problem. How can you now try to defend against an ADE? And that's different kind of ways to do that. We now categorize it in two different kind of more types of defenses. First of all, let's say we have a guard acting on the input a model receives. So let's say a user, a customer can put in any kind of input, but you will now start to analyze that first. So for example, first like to detect anomalies, and say, okay, that's complete outlier. We never expected these kind of inputs. Maybe not go with that. Maybe you can then conduct also transformations on the inputs, for example, using some kind of PCA to get rid of also these more unimportant features, and which make it less vulnerable against ADEs. You can also try to defend by design. That means you're changing how you're training your model. So you have adversarial training, so in a way that, guns and so on, try then to avoid that there is an adversarial attack, for example. So you're minimizing the risk simply that someone finds something. And you can also try to change your architecture of a deep neural network, for example, or remove low predictive features from the model and so on. So again, reducing risk, right? I should note here that all of these will not guarantee that there is no ADE, and often with a sufficient amount of efforts, people can find ADEs. So let's sum up that ADEs are not explanations themselves, but are very closely connected to them actually, right? We have seen that ADEs will help you to get better understanding, and with better understanding you can maybe even construct ADEs and so on, right? ADEs can be generated in diverse settings, and the most important thing actually, which I haven't discussed here in detail, is the distance measure, right? I'm simply saying, yeah, x has to be close to x prime by some epsilon. I have not told you exactly how to do that, and it really depends on the target, on the application, on your data, and so on your model. And that then gives rise again to what is local environment actually. Since we're talking about local explanations. There are different kind of hypotheses we discussed already for the existence of ADEs, and that motivate also different kind of defense strategies that we try to avoid